Hello, Dr. Diaz here, and we're going to continue with the second part of the series of videos for chapter 4. And now we're going to go ahead and switch gears into the chemical formula and understanding what kind of information it conveys. Okay. And we're also going to see chemical reactions and how can we interpret the information that you have there. Good. Okay, so well, the chemical formula is just simply you just have your symbols for your elements with some subscripts that you have in there. So you know some chemical formulas, for instance, H2O, that's the chemical formula of water. Okay. So the chemical formula is just basically telling you what elements are making up water and in what ratio are they combined. So water is made of hydrogen and oxygen, and they're combined in a 2-to-1 ratio. Okay. So if you see a substance in which hydrogen and oxygen are combined in a 2-to-1 ratio, then is water. Okay, good. So the formula unit is actually a concept that applies more to ionic compounds. Okay, and the reason for this is what kind of thing the formula unit, what kind of information the formula unit provides. The formula unit, first of all, well, it provides you the identity of atom or ions, and I put or ions because the ions are the important thing in there. Okay, and it also tells you the relative number, relative emphasis on relative of the type of atom or ion. So in the case, for instance, of water, you have H2O. That is actually the actual number of atoms that you have in a molecule of water. But as we saw before, when we have ionic compounds, you don't have just like one atom of sodium hanging out with just one atom of chlorine. No, you have sodium ions surrounded by chloride ions and vice versa. Okay. So the formula units apply very well to ionic compounds because you're expressing ratios and identities rather than actual quantities or amounts that you have in your particular compound. Okay, so we can think of the chemical formula will always apply to my molecules, and the formula unit is probably something that is better suited for my ionic compounds. Okay, so here we have some examples of chemical formulas. Okay, so this is a chemical formula for all of these compounds. You have hydrogen, you have water, you have sodium chloride, and you have calcium hydroxide. Notice that these two are covalent compounds. So this is not only their chemical formula, but it's also how the molecule looks like. A molecule of hydrogen has two atoms of hydrogen, and then a molecule of water has two atoms of hydrogen and an atom of oxygen. As we know, these are ionic compounds because you have a combination of metal and nonmetals. So therefore, these guys in here will not have this unit called the molecule. So in this case, it's actually better to refer to the chemical formula that we have for these, which is actually indeed a chemical formula. We do not really call that we have a molecule. What we have is a formula unit. So the formula unit for this is showing you that you have a 1-to-1 ratio between sodium and chlorine. And the formula unit for this shows you that you have a 1-to-2 ratio between the calcium ions and the hydroxide ions. Okay. So in the chemical formulas, we can have the complexity of having subscripts of groups of ions or polyatomic ions. And then if we try to think about, okay, how many atoms of this do I have in my particular formula? Well, I mean, you have to do a little bit of math. It's just multiplication. Good. So if you wanted to know how many atoms of hydrogen you have in ammonium sulfate, and you should be able to come up with this name by now, it would be 8 because each ammonium ion has 4 atoms of hydrogen, but you have 2 ammonium ions inside the ammonium sulfate. So therefore, you have 8 atoms of hydrogen. And then in the same fashion, you would have 2 atoms of nitrogen, 1 atom of sulfur, and then 4 atoms of oxygen, which is exactly what you have here. Okay. Notice that the atoms of sulfur and oxygen that you have are identical to the atoms of sulfur and oxygen that you have in just a single ion, and it's simply because you just have the one ion. But in this case, for the ammonium, you have 2 ions. So these numbers in here doubled up with respect to these in our particular ionic compound that we have in here. Okay, good. So another type of formula that we're going to see for chemical formulas are hydrates. Hydrates are a very interesting kind of compounds because what they put together is an ionic compound, in this case, and it would be copper 2 sulfate, together with 5 molecules of water. So what this is telling you is in a unit cell of your copper 2 sulfate, you have 5 molecules of water that are trapped. And this ratio is consistent, okay? We call it stoichiometric. So that ratio is always going to happen. So if you have 1 mole of this, then you will have 5 molecules of water trapped inside the mole of this thing, okay? Good. So notice that this actually gives you some sort of conversion factor as well, okay? Because you can convert from moles of this whole thing to moles of water, or moles of this, of which you have 1, to moles of water as well, okay? So this substance in here is called a hydrate. And if we would erase these 5 waters, let's say you go ahead and you have this substance, this copper 2 sulfate pentahydrate, and you go ahead and you heat it up, the water will go ahead and start evaporating, and it will get transformed in just the copper 2 sulfate straight, or sometimes it's called anhydrous. Good. So that's actually an interesting experiment that you can get to do in the lab. It's fairly simple. This is actually the hydrate, which has a very beautiful kind of bright blue color. But if you go ahead and you heat it up, it actually becomes kind of white and dull. Okay, so this is the form of the anhydrous copper sulfate, and this is the hydrated copper sulfate. Good. Okay, so one thing about the formula weight, or actually even our chemical formula, we can calculate the uh, formula weight of our particular formula that we have, our particular chemical formula. Good. So how do we do so? Well, very simple. If we know how many atoms we have, we just add up the mass of each and every atom that we have inside our particular compound, and then that would give us what is called the formula weight. In other words, kind of the mass of my formula. Okay. So, well, we go ahead and we do that. So then we have that the formula weight for water is going to be the 16 AMUs plus 2 times the 1.008 AMUs that are the mass, the atomic mass for hydrogen, and then you get 18.02 AMUs. So I already told you, AMUs we're just going to see very few times, but going on in the class, we're going to see far more moles, okay? Moles is the thing that we're going to see again and again and again and again, and AMUs are just an idea to introduce the concept of mole after that, okay? And just to have an idea that, yes, the atoms are very small. Good. So the formula weight is actually having units of AMUs because it refers to the actual mass of just the one formula, okay? So in this case, it would be just the mass of one single molecule of water, nothing else. And then in this case, the molar mass would be exactly the same number, but the units are grams per mole. So in other words, in here it would be the mass in grams of 1 mole of water, not one molecule of water, but actually 1 mole of molecules of water. Okay, so much bigger, but again, the number that you have here is the same number, only that the units change. Okay, so this will be the number that we will be using time and time again. Good. So as I said before, the formula unit, it relates very much so to ionic compounds. This is just the crystal lattice of sodium chloride, and the formula unit is just expressing you that there is a 1-to-1 ratio between sodium ions and chloride ions, and it's giving you the mass of those 2 ions. That's what is given to you, okay? So can we go ahead and get, for instance, the molar mass of ammonium phosphate? Yes, it's a little bit more complex because we have to do a little bit more calculation, but it's not that much of a problem. You just have to do 3 times the mass of nitrogen, 12 times the mass of hydrogen, 1 time the mass of phosphorus, and 4 times the mass of oxygen. You can calculate it in AMUs, okay, or you can calculate it in grams per mole. So again, if you want to go ahead and calculate it in AMUs, that would give you the formula weight. And if you want to go ahead and calculate it in grams per mole, that would give you the molar mass. Good. Notice one thing. We call formula weight the mass of one formula unit. And we call atomic mass the mass in AMUs of one atom. But how do we call the mass of 1 mole of atoms? We call it molar mass. And how do we call the mass of 1 mole of formula units? We call it molar mass. So that's another advantage of molar mass. The term doesn't change when you go from one thing to the other. So it's just the molar mass of a compound, the molar mass of an element, the molar mass of an ionic compound, a covalent compound, okay? It doesn't matter exactly what it is. For all of them, it's just going to be molar mass, molar mass, molar mass. Good. So molar mass is definitely a term that we're going to be using far more, but for this exam and also for the final, you need to be acquainted and know what the terms atomic mass, formula, weight, what do they mean, okay? Molecular weight, all of that, you need to know what it means. So molecular weight, of course, would be for covalent compounds, for something that has a molecule. So molar mass, I've already talked plenty about this. It's just the mass in grams that you have inside a mole of atoms. So molar mass of carbon is 12.0 grams per moles of carbon. And again, this is just the average molar mass that you have for it. Okay, so that means that if you have naturally occurring carbon and you mass exactly 12.01 grams of this thing, then you're going to have in there 6.022 times 10 to the power of 23 atoms of carbon, okay? So now we're going to go ahead and switch gears into the chemical equation. So the chemical equation is where you start putting these formulas all together to express chemical change. So it's basically you start with something, these are the ingredients, and this is the outcome. So the ingredients or the starting material, we're going to go ahead and call the reactants. And then the outcome, we're going to go ahead and call the products. And we're going to use just typical Western writing. We're going to go from left to right. So we're going to go from reactants to products. Reactants are going to be on the left, and products are going to go ahead and be on your right. So here you have a list of different things that feature on the chemical equation, but it's much better to go ahead and show it with an example. So here again, we have our chemical equation that is displaying a whole bunch of things. So I will go over the basics of this and some of the details. So the basics thing is, as I said, reactants are going to be on the left and products are going to be on the right. And each one of the reactants and products should have their own chemical formula. So we have in here one reactant and we end up with two products, okay? So again, reactants on the left and products are going to be on the right. So one interesting thing is what this capital delta symbol means. That means that in order to go from left to right, you need to provide some sort of energy. In this case, it's actually heat. The triangle doesn't necessarily mean heat, but it mostly means that. It could be electrical energy as well, or something along those lines. Another kind of detail that we have here is these things that show up in parentheses, and those are the physical states. So this is telling you that this reactant is in solid phase, this is in the liquid phase, and this is in the gas phase, okay? So that would be basically everything that we have here. The only other thing that we're going to show, that we're actually going to see later, is what is the meaning of these numbers. These numbers are called stoichiometric coefficients or balancing coefficients. So balancing is something that we're going to do much later in the chapter, okay? So it's probably going to be on the next podcast. Good. In here, you don't have a balancing coefficient, which doesn't mean that you have a 0 there. What it means is that you have a 1. That is commonly not written. Good. Okay, so then when we go ahead and we have these chemical equations, well, okay, that's fine. Paper can go ahead and sustain everything. You can put in there whatever you want, and it's all good. But we have to go ahead and let's say that we started with this mercury 2 oxide, which was the example for this thing. So what kind of evidence do we have to say that this mercury 2 oxide, after you heat it up, actually changed into liquid mercury and oxygen, okay? So there are many different pieces of evidence that you can collect, okay? So some physical properties can change, okay? Chemical properties will definitely change, okay? And then the substances, of course, they're going to go ahead and become into a new substance because we're talking about a chemical reaction. So here we have different types of evidence that you're going to see, okay? So we're going to have a lab to call chemical reactions that is actually going to go ahead and deal with all of these pieces of evidence. You're going to get to do it, hands-on experience. Good. So release of gas. Okay, there are many types of gases that can be released. Actually, in that lab, you're going to see that hydrogen, oxygen, or carbon dioxide could be released. Okay, but here's an example. When do you release carbon dioxide? When you have some kind of carbonate ion in solution and you add an acid, and then the CO2 happens. Good. So there are ways that we're going to see when the lab comes to go ahead and differentiate the gases. The gases are fairly easy to spot in the sense of, oh, you have bubbles. Yeah, but bubbles of what? Are the bubbles of hydrogen, of oxygen, or of CO2? And sometimes you don't even see the bubbles because the amount of gas is so minuscule that you really don't see big bubbles coming out. But usually CO2 is pretty, I would say, loud, okay? So CO2 is the loudest of the three gases that we're going to see forming in that lab. The other thing, and this is very evident, is the formation of a solid or a precipitate. And this happens when you combine two clear substances, okay? And then in some cases, you will have that this substance has an ion that will go ahead and meet with an ion of the other substance. And when they go ahead and they meet together, boom, they go ahead and they form a solid. The solid will have several different colors, okay? For instance, this particular in here is white, okay, kind of milky. So as soon as you mix a solution that contains the silver ions with a solution that contains the chloride ions, then the silver chloride, which is a solid, shows up. You could have heat that is going to be produced or absorbed. So then if you feel it to the touch that is hot, then heat was produced. But then if you go ahead and feel it that it is cold, then heat was needed. It was absorbed from the surroundings. We're going to have a chapter dealing with all of these heat transfer kind of thing. Okay, you can also measure the temperature. If it goes up, then heat was produced. If it goes down, then heat was actually absorbed from the surroundings. Color changes. I said that these are color changes, but these are different kind of color changes. The color changes that you have here is that the two solutions were translucent, meaning you could see through them, okay? And then you mix them, and now you can still see through them, but there is a change in color, okay? This change in coloring here was for the formation of a solid that showed up, okay? It could be that a white stuff showed up, a yellow stuff showed up, or something like that. We do not have many examples in the lab of this. We have far more of this. Uh, you can have, I already mentioned heat being absorbed or emitted. Light, we're going to have a particular lab in which we will see light that is being emitted, okay? It's actually a fun lab. And then you can have that the electrical conductivity or there could be a magnetic field that is generated or that is weakened as the reaction proceeds, okay? So we're going to have a demo for this electrical conductivity thing. And again, that relates to the electrical properties. So there are very many things that you could have that will go ahead and give you evidence of the reaction. As I said, for these are evident. You can just see them for the most part or feel them as the heat. So here, sometimes the heat is something that you would have to measure with a thermometer because it would be a very minuscule change, very small. So you would need an instrument to go ahead and see it. Sometimes the light is very vivid, sometimes it's not. And these electrical properties, you need some device, some electrical conductivity apparatus to go ahead and measure that, okay? Good. So how do you go ahead and write a chemical reaction on your own? Well, the thing is that we have patterns of reactions, okay? We have four main patterns that we're going to have. And these patterns are going to be called combination, decomposition, single replacement, and double replacement. So it's kind of a Lego type of thing. So combination, what do you think that is? Well, we start with several Legos and we just make them into one. Decomposition sounds like the opposite. We start with the one and we just make them into more. And single replacement is that I'm just changing this piece for this other piece. And double replacement is I'm swapping pieces between things that I already built. Okay. So recognizing these patterns is important to go ahead and be able to write your chemical reactions properly. So we're going to see each one of them in detail. Good. So the first one, as I said, is combination. So you start with two things and you just end up with the one thing. So here we have two examples, the sodium combining with chlorine. So sodium solid, chlorine gas will give you sodium chloride. So this is the one thing, this is the other thing, and this is the third thing that comes up. Or you could have magnesium oxide combining with carbon dioxide to give you magnesium carbonate. Okay, so notice this is a solid combining with a gas to give you another solid. So you having here other types of examples. Actually, it is one combination of a metal and a non-metal to give you a salt. Is exactly the previous example, sodium plus chlorine, metal plus non-metal to give you a salt, sodium chloride. You can have combination of hydrogen and chlorine to produce hydrogen chloride. That's two nonmetals combined to go ahead and produce, in this case, this binary compound, hydrogen chloride. Same idea, hydrogen and oxygen combining, two nonmetals combining to give you a binary compound. Or you could have this last one that we saw, magnesium oxide combining with carbon dioxide to produce magnesium carbonate. Okay. So the next one, decomposition reactions. So in the case of decomposition reactions, again, we start with the 1 and we end up with the 2. So this is actually the first example of a reaction that I showed you. This is mercury 2 oxide, and it's decomposed in mercury liquid and oxygen gas. And this is called calcium carbonate, which is basically what you have in chalk. Chalk is just pure calcium carbonate. If you heat it up, it has to be heated up fairly high, 800 degrees Celsius, and then it starts becoming calcium oxide and CO2. It's kind of a very cool thing to see with some kind of magnifying glass, because the chalk starts having kind of pores that are start growing up everywhere, and it is because of the formation of the CO2 from the piece of chalk. Okay, so here again, couple examples, but here are in writing. So this is the last one that I told you. And this is an example that actually relates to the hydrates. Remember, I told you that when you have the copper 2 sulfate hydrated, then you can go ahead and heat it up and you remove the water. So you start with the hydrate, and then you end up with the anhydrous form plus the water. So you start with the one thing and you end up with the two. So the next type is actually swapping of parts. Okay, so we are going to go ahead and do a replacement of one part or of two parts. So here you have A being combined with BC, and then B is kicked out and replaced with A. Good? Okay, so let us try to think in which kind of circumstances or how is this going to work. Remember, every compound, even if it is a molecular compound or a covalent compound, has a positive side to it and a negative side to it. So if it is an ionic, it's very evident because the positive is the cation and then the negative is going to go ahead and be our anion. Good? So if this in here is a metal, it will tend to replace the metals. If this in here is a metal, but in here you have a combination of nonmetals, it will replace the nonmetal that has the highest chance of being positive. Good? So let us try to see what's happening here. We have a metal here, and then we have an ionic compound. So who do you think copper will replace? The silver or the nitrate? It will replace the silver. So basically what you're doing is swapping these two. The silver goes out of the silver nitrate, and then the copper goes into the nitrate, and then this goes from silver nitrate to copper 2 nitrate, okay, after you have the single replacement. This one is interesting because you can look at water as it follows, okay? Let's go ahead and take a look at it. So what if we think of water as H OH, okay? The hydrogen in here would be the positive part of the water, and the OH in here would be the negative part of the water. So who the sodium will replace? Well, sodium tends to be positive, so it will definitely go ahead and replace your hydrogen. And then the hydrogen will be kicked out and the sodium will go in. So look at the answer, sodium hydroxide, and you cannot have atomic hydrogen just hanging around. What is the natural form of hydrogen? H2, okay? So you could predict these things because you know if I would have to tell you what is in this case the oxidation state that copper will have. So copper, I can tell you that goes from copper 0, which is this, to copper 2 in this particular reaction. So you should be able to write with this plus the information that copper goes from copper to copper 2. You should be able to write this just fine. And then this one, same thing. And here is easier because sodium only has one oxidation state, which is +1. So if this is +1, we know OH is -1. So then the formula of that would be NaOH. And we know that hydrogen cannot be on its own, so it would be just H2. Okay, good. So let's go ahead and just refer to a couple of examples. You can have replacement of copper by zinc. Notice what you are replacing with what. You were replacing a metal with a metal. So that makes sense. So the copper was originally in copper 2 sulfate. That means that the copper 2 is going to become just metallic copper. And the zinc is just going to become zinc ion. Good. Replacement of aluminum by sodium in aluminum. So notice the recipe. You're replacing a metal ion with a metal, okay? So the metal will become a metal ion, and the metal ion in turn will go ahead and become a metal. So then we finally have double replacement reactions. So in the case of double replacement reactions, you have usually two ionic compounds that are reacting. So let's say you have cation, anion, cation, anion. So what's going to happen? Just swap of the ions. The cation of this one will go with the anion of the other one, and then the cation of this one would go with the anion of this one. And then you have the corresponding result. So it could, as I said, it's very common in ionic compounds, and that's what you have here. This is lead to nitrate, and this is sodium chloride to give you lead to chloride and sodium nitrate. And then this one that you have up here is actually with a covalent compound, okay, and an ionic compound. But we know that in this covalent compound, hydrogen is the one with the positive charge, and then chlorine would be the one with the negative partial charge. So then the hydrogen, of course, will go ahead and go with the OH to form water, and then the sodium would go with the chlorine to go ahead and form sodium chloride. Here, I want to bring your attention to something. If you combine lead-2 with chloride, what is the formula that you get? And this is something that we learned a few chapters back, okay? The formula that you get is PbCl2. Why? Because this is +2 and this is -1. So this is the formula. Good. Notice that some people would tend to say, okay, well, but if I have just one lead in here and then one chloride in here, wouldn't the formula be PCl? No, because the formula doesn't depend on you having 1 and 1 on your original formulas. It depends on the charge of the ions themselves. What is the correct formula of a compound? So in similar fashion, notice how many nitrates you have here. You have 2. But how many sodiums you had originally in here before these 2 showed up? And then, of course, the 2 is associated to this idea of balancing, okay, that we're going to go ahead and see later. So your formula for your product is not NaNO3 because you have 2 NO3s in here. No, it's NaNO3. Why? Because Na has a charge of +1 and NO3 has a charge of -1. So therefore, the correct formula is NaNO3. So one thing that is crucial on this endeavor of writing chemical reactions, you first write your correct chemical formulas, and then you figure out why do we have these discrepancy of, oh, I have 2 nitrates in here, I just have the 1 in here. And you fix it via this coefficient that you have here that is called a balancing coefficient, okay? So we're going to do a little bit more of that on the next podcast, okay? So when we have this chemical reaction, which is fairly simple, you just have hydrogen gas reacting with oxygen gas to go ahead and give you water, depending on the temperature, would be a liquid or a gas. So then, okay, elements, we said that if I say hydrogen, then it's H2. If I say oxygen, then it's O2. Good. So, well, this reaction in here it's not balanced because we have two hydrogens in here, two hydrogens in here. Okay, that's good, but we have two oxygens here and one in here. And again, you can go ahead and change things into some other things, but we cannot make them disappear or appear for that matter. Good. We have to keep a balance of the matter in here. So we have two hydrogens. We need to have the two hydrogens, which we do already. And if you have two oxygens, you need to have the two oxygens, which is a problem because we don't. Okay. So we go ahead and we put those twos in there. So what those twos are going to go ahead and do, notice that this multiply the oxygen times two, balancing the oxygen, and it didn't really do anything to the hydrogen, to the balancing of the hydrogen, because it's still balanced. Okay, it was balanced and it's still balanced because you multiply both hydrogens times two. So now you have four hydrogens on each side, and you have two oxygens on each side, and therefore your chemical reaction is fully balanced. Okay, good. So this would be the end of this second podcast for chapter 4, and I will see you on the next one. Bye bye now.